Yeah. So so can anyone confirm that my screen is visible to you or not?
Yes, yeah, it's visible.
Yeah, thank you. So yeah, so today's topic will be mostly unified shared memory. And so before moving into that, let's jump back to the previous lecture. So previous lecture you have discussed about the buffer, right? And buffers and accessors and how to use that. There was one question in which it was there. So for finding whether a particular elements exist in an area or not. So yesterday's answer was you guys had given the answer that we can use GPU for this process, right? I would want you to guys engage with me. So you can unmute and give the answer. It's fine. Hello? Yeah. So you guys have only told that whether a particular elements exist in an array. So let's say what do we mean by particular element exist? Suppose that if a element has a value true. Suppose you are given an array, and if any array in a, that if any at any index, if that value is true, then we will consider that element exists or not. Now let's move ahead to how can we code this into the GPU. So do you have any idea how can we do that in the GPU? Have anyone any suggestions or any ideas or how to implement this thing? Anyone could have answer. It's fine. I mean, even if it's wrong answer, I mean, I also particularly had given the wrong answer for this one. That's why I wanted to take this. So, but answering would be, I mean, beneficial for you as well. Anyone? You can also write your ideas in the chat if you want. No one? Okay, then let's now begin. So let me show you the what we can do here. So suppose we have a buffer. So we have taken the data and we have stored it into the buffer, which is the thing which I will not show you now because you have already understood it yesterday. And you have taken an accessor for that queue. Now, if that data accessor is fine, then they will also create a buffer for the flag. So suppose that if the flag is true, then there is an element exist in the array, or otherwise it's not. So now what we can do is if the data accessor is equal I, then the flag accessor will be true. So do you think that this code will work or do you think that this code will not work? So do you have any ideas about how you can do it? Yeah, Prasanna. Uh, so wait 1 second. If result. So Prasanna, do you think that we can use printf in the Sycl first of all, in the from the
Oh,
GPU perspective?
okay. Sorry about that. I didn't realize that.
Ye- Yeah, so you should have considered about a flag perspective.
Yeah,
Yeah,
CUDA allows printf.
yeah, CUDA allows printf. Yeah, definitely. But I do Sycl doesn't allow printf. For Sycl, if you want to do that, so you might have studied in the OOPS concept the outstream and all right
Yes, O
in
stream.
C++. Yeah, so overloading we have used it in class. If you have done OOPS in the C++, so using that method we can do the out printf. Yeah, C out and all. But we can directly use printf in DPC++. Yeah. But do you think that this code will work fine? So what would be do you think that this code will work fine? Uh, Yeah, you can answer, Prasanna.
Well, I don't know. The uh, in Sycl how it actually treats start flag is equals true.
The start. So what happens is, just imagine a x. So accessor is like a vector kind of thing, right?
Okay.
Okay. So I have just created a vector of size 0, of size 1, sorry. So what will it will point? It will just point the zeroth index of the flag accessor buffer. This is what it is.
Okay.
It's just as it is. So do you understand what the flag accessor is, right?
Yeah. Yeah. No. Yeah.
Yeah, now you got it.
Yeah.
So what do you think that is this approach of mine is correct or not? I mean, anyone else who could also answer. I mean, if just that is just two option, yeah, it's correct or either it's not correct. I will not ask you why it's not correct if it's not correct. If it's correct, I will not answer you. I will not question you why it's correct. You can just type yes or no. So yeah, I mean, so what you can say that this code will work correctly. Now, why do it work correctly? So, so what happens is that let that data accessor has even at least one value one. Any one has one value, right? So it will just go and make the flag accessor as true. Anyone can do it true, and we are not making that the flag other element could also make the flag accessor values as false, right? So anyone can make a, so if any one of them is also true, any one data accessor is true, then it will make the flag accessor as true. Hence, this code will work correctly. It's, I mean, it's really brilliant that these two lines can just figure out what would be the code time complexity will be just run in big O of one. So that's how we can just reduce this large problem which might take in the CPU the big O n time. We will just reduce it down it to big O of one. Now let me ask you one other question. What should be the initial flag value? I mean flag accessor value for this question. I mean for this approach. What do you think would be the initial flag value? I mean it's obvious that it should be false, right? So if the initially the flag value is false and then you are making it true. So you will get to know that there is a particular element exists in the array or not. Does everyone get this, right? So now let me ask you a follow-up question. What if we want to check whether all the elements are having value as 5? What do you think now would happen? What can we think about how to approach this problem? Does anyone have any idea that how can we approach this problem? See, I would suggest you to give some ideas, even if it's very small idea, even if it's wrong. So you just have to be implement on this only. You have to just make small changes here. Then this follow-up question will be correct, will be implemented. Yeah, yeah, okay. So if the flag exercise is equal to then Saurabh, what should be then the data flag accessor value equal to true or it should assign the flag accessor as false? It should be true. So let me design one test case, right? Suppose assume that all the elements are 5, right? And on last element, on apart from the last element is 6, right? So now what will happen is all the element all the element will make this flag accessor as true, and then the last thread will make this will make this so even if the so what happens is the five all the elements are 5, right? And the last element is 6. So now what happens is suppose this last element, first check this condition, that if data accessor equal to 5. So it will not consider this statement, and this it will just complete its termination. Now after that, some other thread will start working on it, and it will check that the data flag accessor equal to 5, and it will make it true. Even if the answer is not true, then also you will get this as true. So are you getting my point, right? Or should I explain it in the detail? Yeah. The problem will occur. Now, what do you think, that how can we resolve this problem, right? So this is the problem which we are facing. And one honestly, then this is very interesting topic. When you are when you are working with parallel concepts, right? This is called the data race problem. We might have to verify this at every step, that we might have to check, is there data race occurring or not, how can we resolve this. So this is kind of similar problem to a data race problem. Now how can you resolve it? Do you have any idea? Or someone else can give any idea about how you think that you can do this, how can you solve it? You can also unmute your mic and answer it, don't, it's fine. Yeah, so let me help you with this. So how can you do that? Suppose you make this as a data accessor not equal to 5. So that's a different approach than we are doing previously. Previously we are doing just if it's true, then we will make it set true. But now there is different concept. If it is false, then we will make the flag accessor as false. So now what will happen? So suppose we will just take the previous example which we are taking. All the elements are 5, and one of the thread has 6. Now that the thread which have a value not equal to 5 will only go inside the if statement, and it will execute that the flag accessor equal to false, and thus this approach will give the correct answer. But the here the flag accessor value should initially be true, right? So suppose if the flag accessor initial value is true, now what happens if we will just compare the data accessor. Every thread will just check that its value is not equal to 5, and then it will just make the flag false. Even if there is one element whose flag accessor whose data is not equal to 5, then it will just make the flag accessor as false. So this is how we have overcome the data race in the different way. So these are the small concepts which you might which might be very interesting, but if you look very carefully, we can solve such great problems here, definitely. So also, also I would like to add one more point here, that this is any kind. So if any is true, then it is true. This all are true, then it is false. So what we are doing in predicate logic, and also in similar, we are doing just check if there is only one false, then we will make it false. So that's the concept we are using. Now let's jump back to the unified shared memory. So what is USM? It is a pointer based memory management, right? So have anyone worked in CUDA or heap, in any other uh, backend for parallel processing and all? Is there anyone who have worked apart from in the CUDA? I mean, OpenCL. I know that Prasanna has done it because he has sent me the CUDA code. Yeah, so that's so yeah. So you might be so in the CUDA and OpenCL also have a pointer based memory management system. Yeah. So what so yeah in the so let's jump to pointer based memory system in DPC++. So there are three pointer based memory systems: device, host, and shared. So it's pretty simple to understand that from their name only. So let's understand in detail. So device can be accessible to host. Can no Device can be accessible to device. Yes, we can access the device only in the device. I mean the type. if you are assigning the so this is the basic malloc syntax that so we are using the malloc in C++ to for pointer based assignment, right? Here is just malloc device. The syntax will be same. I will walk you through the syntax how it is written. But if you are assigning a memory using malloc device, it will be only accessible to the device. So what do you mean by device? GPUs and all. So CPU cannot access the pointer based memory which we have assigned using malloc device, right? The host memory can be done using host, can be accessed using host and device. But here you might think, okay, let me come to an interesting thing afterwards. So there is also shared memory. It can be also be accessed using host, and it can also be accessed using device. Now, so there are two memories, host and shared. Both of them can be accessed using host and device as well. Now, what do you think? So, why do we need two memories separately? What do you think is the difference between this host memory and shared memory? Does anyone have any idea about? I mean, so does anyone want to comment why it's that? So, yeah. So, what happens? Yeah,
Yeah, host memory is necessary to do the data transfer between CPU and the device, and also manage the overall program flow. But it's the or what you call device
yeah,
memory
shared
is
memory.
where
Yeah,
only the device is using.
yeah,
And though it's accessible to host, well, actually, it's not accessible to host.
yeah,
So
yeah. Shared memory is accessible to host as well as
yeah,
device. So why do you think what do you think that the difference between host and shared memory? Because the both are
well,
accessible to host as well as device, right? Yeah. So so let me help you with this. So the host memory is only assigned. The host memory assigns the memory only on the host part. So it will not assign the memory on the device part. Now what happens is as you use the host memory in the device code, it needs to fetch the data from the host memory. So it fetches the data using the so there is a from between the host and device there is a PCI Express bus. So using the bus that host access the memory and then then if there is any write and all then you again send back the memory. So between the CPU and GPU calling there will be a lot of latency. So it wouldn't be I mean efficient to use the a host memory in the device if if we are not assigning if you are not if you are frequently accessing the memory, right? So if you are frequently accessing the memory, it's not beneficial to use the host memory in the device code because it just need the PCI Express gateway, so it will just reach, then it will again send the data. Whereas what the shared memory do, it creates the data in the device as well as host. Now it will now whenever the need, it will just mem copy this from here to here. So it will just copy the data from device to host or host to device after whole iteration is completed. While as host, if you are just specifying a host variable in the device code, what happens if it will at that particular moment it will go and search this variable is this value from the BCI bus expression and then it will give the answer. So the latency increases in the in the host based memory, right? So this is the basic difference between host and shared memory.
yeah,
Yeah, do you
if
any? Yeah,
there's any need for sharing data between the threads, that is one of the needs, and inter-thread communication for whatever
yeah,
synchronization or uh, inter-thread communication needs to happen. Shared memory can be leveraged.
yeah, sure. So what would be the developer view? Developer. So according to the developer, suppose this is CPU, GPU, would be host memory. This is the GPU memory. So this is GPU means device memory. And then for the CPU and GPU, so if you are using shared memory, so this shared memory is also called unified shared memory. So if you are using that, then the CPU and GPU can directly access that unified shared memory, and then we can just use that, right? So how do you? So this is the syntax of for allocating the memory for device, host, and shared, right? So this is the basic C++ concept. We can also use that malloc host here. Apart from malloc, it's, I mean, the both of them works completely same. So for the malloc device, this is the integer. So this is the int. Then we have to, for the device, you have to also pass the q. For this, q, this is done. So q is that, I mean, which for which device we are assigning this. So we are using this memory based pointer, right? So also, yeah, so for shared also it's similar. We can also use the static cast syntax also. I mean, it's fine. So you can just go through this. So yeah, now we will just use, so they are basically, we are just basically dividing into two parts. One is shared memory, one is host and device memory, right? So yeah, so let's consider that example for without using shared memory. So unified shared memory is basically shared memory. So let's take an example without shared memory. So first you will, so first you will get the queue, get the device, and you can just print this way that this is the device that been assigned to it. Then after that, what you can do is initialize data on host. So what it will do is, so on the host side you are assigning the data. So this is the syntax that we, this is also the syntax that we can use to initialize the data on the host part. So I mean, this is, so you can also use this approach. I mean, it's completely fine. It's up to you in whichever way you find. And we are assigning each data item on the host as I. So I mean, zeroth index as zero, one index as one value, two index as two value, and so on, right? Now we are assigning device side memory. So now we are allocating memory, malloc device memory for the device side. And then, so this is the basic syntax that we have looked earlier only. So malloc device integer means integer, I mean, n means what is the length of the array which you want here. So nth here is, so this n. So we have just taken the constant int n equal to 16. You can just change it also. And for this queue you're using, you are allocating this memory. Now what comes here now, as the shared memory manually copies the data from host to device, uh, but we are not using the shared memory, right? So we need to manually copy the data from the host to the device, because in the host we have initialized the data as each index should have I data, right? So we have to just copy this whole data array into the device array. So yeah, so there is, so we I have just written a code, I mean, how to so it will just copy memory from host to device. Now what it does in this queue, it will submit a mem copy. After from it is submit a mem copy to the data device from data. So it will so this is where it will go from this. So to, from, and then the size of the data which we want to share. It's I mean, if you have worked in the CUDAs and all, it is the same as that only, from, to, and then the size of the array which you want to copy. So remember, there is dot wait here. We will come back to it in today's lecture only. Why do we need dot wait here? So just remember this dot wait. I will explain you why it is needed. So now what we have done is we have copied the memory, copied the data from host to the device, and now we can do some computation on the device. So suppose we have done some computation, like just make the square. Every element has taken its square. Notice that here is also dot. Here there is also dot wait, right? and then they copy memory from host to device again. So now we want to access that this kernel has done some work. How can we analyze it? We cannot, so just now we have discussed that we cannot print something in the device, right? So what I have done is I would copy back the updated data from the device to the host. So notice, so okay, so here the syntax should be the data should come earlier and the device should come afterwards. Yeah, it's a small mistake, I will rectify it. So the data should come here and data device should be afterwards, and then you can access the data. And if you print the data, then it will be each element, each index will have its square. So it's 0 0 for one index, it will be 1, two index it will be 4. So this is the basic structure of the code which we can use if you are not using without if you are using uh, pointer based approach but not shared memory. So do you have any problems in this, any doubt or any question regarding this? Do anyone have any questions or? Yeah, yeah, yeah. In the, yeah, so it's fine. Yeah, it's correct person. In the CUDA, we have explicit deallocators. In Sycl also, we have to deallocate this memory. If we are not able to deallocate this memory, then that will be problem. So yeah, I will just in the chat how can we deallocate the memory. I won't return. So for the device, for the host memory, we can directly use the free, and then in the braces we can directly, yes, write the data, right? But if you want to so I will send the how to free the variable which is of the device type, right? We have to free the, if we are not freeing the space, then it will be in the heap. And as you know, basic concept of C++, then at some point the memory will be full, and so the heap will be full, and then it will give error, right? So you are correct. So we need to free the data. So apart from them, is there any doubt or any question? Also in this, so the free which I have typed in the chat box, the free, then the variable name of the array, and then q. So the q is required because it tells for which device it will the memory based pointer based memory is assigned, and from there you wanted to free the memory. So the q is also required in the free. Yeah. So is there any doubt? Okay. No doubt. So I'll consider it as there are no doubt. Now we can move ahead. Let's take an example with unified shared memory. So we have seen here that we have to assign the host side, then device side, then manually copy, then again do some computation, then again copy. So let's see what happens in unified shared memory. Suppose in this shared memory kind, unified shared memory, uh, wait 1 second, right? So let me come here only. I don't know why the slide. I think the slide got messed up. So yeah, what happens in the unified shared memory is that the basically we will assign a pointer to the we will assign a memory using the unified shared memory code, just like this, and we can directly compute the kernel part. We don't need to create another one for host, one for device. After this, we can directly compute this part, and then we can directly use this approach. I don't know why. I think there is some mismatch from the slide when I have downloaded. Yeah, but so basically, what I'm trying to say is, just wait 1 second. I will rectify it. It's possible. Yeah. So yeah. Okay. So for the shared memory, we only require this initializing the data. So we are assigning this data as a shared memory. So it will be in host as well as in device. And then we are using this, we'll just update this kernel. We don't need to copy the memory back to the host. So this is the code which we will require. We will not require this memory allocation for the device memory memory copy from host to device and device to host. We'll just require this initialization of the shared memory, and then we will just compute it. So it will be that simple. We'll just require so the code will be reducing so far. So in the code, the number of lines in the code is reduced. Also, the debugging reduces. So if you are using the shared memory, right, then you don't need to copy the data from host and device. And sometimes if the developer might forget to copy the data from device to host, and then he's doing some computation, and then so it's hard to debug the code afterwards. So yeah, so unified shared memory can be used in that case. Okay, so is there any doubt? Okay, so now when can we use USM? So you have looked for the buffers, right? As well as now you have also come to know the slight concepts about the pointer based memory, right? So when can you think why should we use USM? So suppose your code was earlier written in C++, in sequential, right? Now you wanted to make it in parallel. So if you are just changing all the variables using the CUDA, I mean malloc shared memory, unified shared memory, then yeah, I mean it is practically done, right? So we just need to make, so we don't have to worry about the data now. Whole data would be covered as it is. While in the buffers, if you are going through buffer side, then you will just create one buffer. Then every time you are accessing, you need an accessor from the device side. You need an accessor from the host side. If you are using, then you will need an accessor. So yeah. So if you are porting from C++, it would be much more efficient. I mean, much more faster, and it will minimize the changes if you are using the unified shared memory, right? Because it will just change it. We don't need accessors and all. Okay. So, yeah, when control data, okay. So let me just clarify one more thing here. That so if you are using two memories, like host memory and as well as device memory, then it is called as explicit unified shared memory. So it is explicit, right? So both of them are separate. That's why it's called explicit unified shared memory. This is explicit, and if we are using the shared memory, malloc underscore shared, then it is called implicit unified shared memory allocators. So if you are using explicit, suppose if you are using host and device as two separate memory, now what o- now what we can do is, if we want only half of the area to be copied from host to the device, then we can also perform that. Suppose I want only even indexes of the data from host to copy into the data from device, then also it can be done via through using the, if you are using the host and the malloc in for there, so it can be manipulated. So if you are using this concept, then you can explicitly unified shared memory allocators when control data movement is required. Yeah. So so buffer doesn't allow you to do this thing. So buffer, you just create an accessor and then you will use it. While in the USM, if you are using host and device separately, you can control the data movement here and there. So you want the data from at this point here. So that can be beneficial sometime. So is there any doubt until now? Okay. So what are the drawbacks? So there should be some drawbacks of unified shared memory, right? Shared allocator is not indicated to provide peak performance. Yeah. The so the shared memory, the malloc shared which we are using, are not always intended to perform peak performance. It will just give you a boost up. It will be easy, it will be minimum, it will get you functional quickly, right? So it's the second point, but it will be not it is not intended to provide peak performance, because similarly the thing which I have told you right in the earlier also. So if you have a memory on host and as well as device, you can control the data movement and everywhere where is the data going, and then you can make the performance better, optimize the performance. You can use some optimization techniques and all, and then you can do that optimization, and then the performance increases. But if you are using the shared memory, malloc shared, then you cannot do it. Then you're not in control of that. That's why the shared allocation is not intended to provide peak performance. Yeah, it will provide a good performance. It will provide better performance than CPU, but it will not provide peak performance. Also, data dependency needs to be taken care by the user. Now, what is this data dependency? Mm, So, in the buffer, the data dependency concept was not there. Between the kernels, the data dependency was taken care. Now here comes the data dependency, and we don't know what is the data dependency. So let's just take an example of how the data dependency can affect us. How when the developer needs to decide using implicit versus explicit. So yeah, implicit versus explicit. Yeah, okay. I will clarify the doubt. So if the developer wants to control the data from where the data should be moving, and if suppose what happens in some scenario, right? Suppose there is some work done by the CPU and some work done by the GPU. Now we want to collaborate both. So some of the task has been done by the CPU and some task has been done by GPU parallelly. Now because CPU can do some sequential task faster while the GPU can do parallel task faster, so we are combining this both. Now you don't want whole memory data to be colliding or to interfere with each other. The shared memory will give the poor results when these both are happening in the parallel. So at that moment, we can use the explicit USM. So if there is separate memory for host and the separate memory for the device, then we can easily configure from this size. We can just put the here memory, and so thus we can use so then the developer can decide between which kind of USM which he requires, right? Okay. So is there any other doubt apart from that until now? See, guys, I also wanted others to join in the conversation. It would be helpful for you as well. Okay, so I'm assuming that you had no doubts. Okay, so now let's jump. What is the data dependency? And we don't know what is the data dependency. Suppose now we will take a look into how the data dependency is affecting us. So I want all of you to answer. What will be the answer for this? So one basic concept I wanted to before you go and solve this, a basic concept one I was wanted to tell you is that what the buffer does. In the previous lecture, you understood that the buffer will create a data dependency graph of each kernel, and then it will launch the kernel in that way. Suppose kernel C depends on kernel A, and kernel C also depends on kernel B. So until kernel A and kernel B has been completed, kernel C cannot launch, right? The buffer internally manages this. But what happens is the unified shared memory doesn't do that. Unified shared memory doesn't internally handles the data dependency. So yeah, so this is what I wanted to tell you. Now I've just created a data of the shared malloc shared using the malloc shared, and I will just run two kernel. One is just adding the data into +2, and other is adding the data values to +3. Suppose initialize. Suppose the data all the data elements are initially 0. Now what do you think will happen? What could be the possible answers for this? Can anyone guess? Is there a is it is will it give one answer or will it give multiple answers? How many answers are possible for this if you compute this code? I want everyone to answer this question. So again, I want to clarify that the buffer internally creates one data dependency graph. Suppose that kernel kernel C depends on kernel A, and kernel C also depends on kernel B. So until kernel A and kernel B are completed, kernel C will not start executing. But unified shared memory doesn't do that. If n equals to 3, then all elements will be 2, 2, 2. Uh, no, we will not go into the that is correct. But let's assume that n is very large. N is suppose 10,000, 1 lakh. Now what will it do? We'll come to this concept tomorrow. Sure. Suppose n is very large. It is 1,000, 10,000. Yeah. Then what will it do? What are the answers possible in that concept? Why do you think it will add 2 in every element? Why can't it add 3 also? Sort of. So I want everyone to answer. Yeah, for this statement it is adding plus 2, and for this statement it is adding plus 3, plus equal to 3. Yeah. So after this whole code execution, what will be the values at that? What could be the possible value for the data I? So you're getting this concept. This is this kernel, right? So this is q dot parallel 4, and this is the range 1. So you got it yesterday only. 5. Is it the only answer, Saurabh, or there could be multiple answers possible? Or do you think that this is the only answer possible? Okay, yeah. Any other guesses? Okay, so it turns out that the answer could be 2, answer could be 3, and answer could be 5. So yeah, so this is how this is interesting, that how do you think that 2, 3, 5 answer could have come? So now what will happen is, suppose it doesn't have any dependency graphs. Okay, so then the CPU will read this and it will launch its kernel to the device. Now CPU will move ahead, and it will not wait it will not wait for the kernel to complete. Again, the CPU will read this data I plus equal to 3 kernel, and then it will again launch that also into the device. So there are two kernels running in the GPU. Suppose we are running code in the GPU. So both of the kernels are running on the GPU. Now what will happen is that, so this plus equal to is further divided into data plus 2 equal to, so it is further divided into data I plus data I equal to data I plus 2 internally. So suppose if you have read OS, right? In the OS you have gone through the some basic concept that all the instructions are further divided into sub instructions. And so this will have a load data I, then it will add the data I plus 2, then it will store the data. Right, these are the basic sub instructions that we have studied in the our COA and COA, right? So this will also do that, this will also do that. Suppose now there are two kernels running. Suppose we are talking only about the index 0. Suppose we are talking about only data at index 0. Both of them have load the data at the same time. So both the kernel will get data 0 as 0. Both of them will add plus 2, or this will add plus 3. Now both of them will store the result. Now what happens if both of them are storing the results? So this is storing 2, this is storing 3. So there can be so there will be data race, any one will be stored, and so we can get either 2, either 3, or what happens if uh, yeah, we can. So now, no, we cannot look at a very large memory in the USM. There are some basic concept, some basic limitations for the USM. Yeah, but it's just for the example which I was saying. So it's just for that only. Okay. So for the data, so there are two possible answers, 2 as well as 3, right? Both of them are loading the data 0. Both the kernels are updating. This is will update to, this will update to 3, and then both of them are trying to store the data. Now only one can store. So as there is a data race in the data race, there is only one data will be persistent. So either it will be 2 or either it will be 3. So there are two. So there is two also possible. Then 3 is also possible, and then we are assuming that then how can we get the 5? Suppose the one kernel has completed all its execution, then it is stored the value 2. Now the second kernel has started, and then it will complete the execution, and then it will store 5 because it will add 3. So there are three answers possible: 2, 3, and 5. All these three answers are possible in this malloc share device. So is there any doubt or any questions? So are you guys getting how 2, 3, and 5, all three answers are possible in this? Everyone else? Yeah. Okay. So yeah, great. But how to verify this? So DPC++ provides three data to avoid data dependency. It provides three ways: the dot weight, in order, and depends on. We will look each one in detail now. Okay. So dot weight. So what it will tell, so when the CPU starts reading this kernel, so then it will launch the kernel and then q dot wait. Now the CPU will wait here. At this point, the CPU will wait until the kernel's execution, the all the previous kernel execution for q has been completed. Until that point, the q will wait here. So suppose if I have written this kernel, and then I have used the dot wait. Now the CPU will read this. CPU will read this, and this will wait. The CPU will stop its execution here until that kernel that the queue is empty. So until the queue is empty, it will be stuck. The CPU is also stuck here, so it cannot launch this kernel. So is it clear how the dot wait will work? So it will just launch one kernel, and then we will launch the second kernel. Okay. Now, can you identify where could be the problem caused in this dot wait? So there might be some problem caused by using the dot wait, right? So what could be the problem caused by the dot if you are using this dot wait? So I mean, we can also directly. So this is also one clear syntax that after kernel we can write q dot wait at any point of time, or you can directly use this after the kernel. You can just write dot wait. This both are valid. So can you have any can you give me any case where this will face some challenges or face some problem? Do you have any idea or any thought about how can this face some problem? S- Suppose let me give you it. Using this, suppose if you are doing two kernels and both of them are having different data. So this is working on data 1 and other kernel will be working on data 2. So will it create a problem? We are using this. I will same copy this and paste this, and I'll just add data 1 here and data 2 there in the sequence, in the one after the other. Do you think that it will face the challenge Challenge, I mean, so it mean it will reduce the performance or anyway. It shouldn't do some task. Shouldn't uh, provide the data synchronization where it shouldn't do it. Yes, yes, right. So what will happen is, suppose if I just copy pasted this below only, and there is one data one, and also there is data two. So there are two kernels working with data one and working with data two. Now what I have done is, and they are both in the same queue dot wait. Now what I have done is I have made the CPU stop here dot wait after. So as I have written the dot wait, it will be stopped. So the CPU cannot move ahead until this kernel has completed its work. While what should have happened is that if both the kernels are working on different data, we can just parallelly run both of them, right? So did you guys get that? Yeah, I actually I don't know how internally it is implemented or not. So it will just wait the CPU. I don't know. I will tell you after the class or something. I will just add in the pip slides on how it is done. I don't know. Yeah. So do you guys have clear that how can q dot wait may create problem if not used correctly, or should I explain this once again? Any thoughts, any suggestions? Should I move ahead or should I repeat one? Yeah, okay. Yeah, okay. I will repeat the same thing. Okay. Suppose there are two kernels. I am working with two kernels. Suppose assume this is kernel A, this is kernel B. So, okay. Just assume in this way. And suppose I am working. So suppose this kernel is working with data one and this kernel is working with data two. Both of them have different data items, right? So now what should have happened, that they both can run parallelly, right? I assume that all the threads are working on one data item. So this is adding, each thread will add its index plus 2, and this will add each thread will add its index as plus 2. But both of them are working on different data. So they should be run parallel, right, Saurabh? To give the performance, they should be running on parallel to each other, right? But what will happen, that if we are after we have, so in the CPU we will write this kernel then this kernel, right? So in between, if we have used dot wait or we have used this syntax, right, the syntax, then what will happen is, after writing this kernel, then the CPU will stop here. CPU will not launch this kernel until this kernel has completed its task. So it will not create the problem, but we have unnecessary add the synchronization where it is not required. So we have synchronized kernel A from kernel B using the dot wait where it is not required. So if we are using the dot wait, yeah, second kernel, yes, the second kernel will not start its execution until the first kernel has completed its execution, right? That's how we have. So remember, if we are, it depends on the developer where he writes the q dot wait. It depends on us. It's just slightly. I'm giving you hint so that you don't face the problem. Yeah, so you can optimize your performance and all. So yeah, just remember this, that while using the q dot wait, you have to figure out that where should you use q dot wait, so this kind of problems or this kind of situation will not occur, right? So did you guys get that? Did everyone got that? Okay, so let's move on in order. So yeah, so this is the second kind, how we can avoid the data dependencies if you are using USMs. So we will write this in order in the queue property. So while initializing the queue, if we write the properties queues is in order, then what will happen? Any kernel which we will assign to this, it will serialize all the kernels. So this is also facing the same problem which we have talked earlier, right? So what will happen? So now you don't have to necessarily assign q dot wait. Now what we'll do? Every kernel which will be like q dot after that parallel for everything which we have written in the q dot for q dot after that will be run sequentially. So after this, after this, after this, after this, after this, after this, after this. So execution will be non-overlapping, even if the queues are data dependent. The same thing that we have talked. Suppose this is one thing and this is one thing, and if we are used the in order, even if this both of the kernels are independent, they will run sequentially. So after this is completed, then only this can start running. This is the side effect of using in order. But suppose if you're only working on one data items, and then you don't need to manually add dot q dot wait everywhere you may require, then of course you can do this. I mean, then it would be completely fine. But yeah, it's so in order will execute everything sequentially, even if the data is not dependent on each other. So here also you have to, so here also there are benefits as well as there are side effects. So here you don't have to write q dot wait every time. It will just take one by one. Even if you are copying the memory from one way to another, then also it is also done in order. Until that the memory copy has not done, it will not start executing the other kernel. So that's how this in order will work. It will just start sequentially, and it will do every task, it will do every kernel task sequentially, right? Okay. Now depends on, this is the thing. I mean, so this is the thing which I also use, and you might also use that in future. So will that be fixed by writing just one to a dot wait after second kernel? Saurabh, and what are you saying? I didn't get your question. Will this be fixed by writing just one dot wait after second kernel? Or suppose if we are not using in order, so in this slide, okay, right? You're talking here, right? In the dot wait slide or in this example slide? You can also unmute your mic and speak. It's fine.
Hello.
Yeah,
When you told the problems of using wait, that the
yeah, yeah,
second kernel will have to wait. I was talking about that this slide. Yeah.
yeah.
So how will you
Okay.
fix this problem? By just writing one wait after the
Yeah,
second kernel.
yeah, yeah, yeah. You will not
Okay.
write q dot wait after the first kernel. You have to write the wait dot after the second kernel if it is dependent on some, if these both are dependent, even if
Okay. Okay.
they so you have to manage the dependency by yourself.
Okay.
Yeah. So okay, so this also depends on, just wait. So what this depends on is, suppose you have written this kernel or this task, right, kernel task, and now you have assigned this to e. So you so this is what depends on does. So this until so we have assigned this whole kernel as e, and until this h dot depends on completes, it will wait at this point. Suppose we have written various kernels, right? So how this will be useful? So first of all, I will just explain you the code. So we have just taken this whole kernel, and we have just used auto e. So I mean, you can also search, I mean, if you want. Also, I mean, I won't suggest you, but if you want to see what is the thing here, you can just Google it and it will be there. But then I've just taken this whole kernel task and assigned it to e. and the whole kernel will be launched by the CPU at this point. Now what happens is, so this kernel task is dependent on this kernel task, right? So while submitting this kernel, we will just say that it depends, h dot depends on e. So at this point the CPU will wait until event e is completed. So the CPU will wait or GPU will wait. What happens? So that's the thing I will there. So this is the thing which I'm giving you as a homework. I mean, so if you just figure out which one will wait, CPU, either CPU will wait or either GPU will wait. So this is the thing that I think you should try out. Also, just see what is which one will stop at this moment. So let's consider either CPU, either GPU will stop this execution here, and so this will be so until this kernel is not completed, this above kernel, then this bottom kernel cannot start executing the code. So this is how it depends on the kernel. And also so suppose this q1, yeah, so suppose there are multiple kernel tasks, this kernel depends on multiple kernel tasks above, right? So we can just like auto e1, auto e2, and just we can just copy paste this h dot depends on e1, h dot depends on e2, h dot depends on e3, and so on, right? Also, I mean, so this is the one way which we can do this. And also we can, if we are using dot parallel for, then we can also be after range one, and we can just write e. I mean, so for the this e, if we are writing this, then also it will just consider this as depends on. Okay. Also, I mean, if more than one es are here, then we will just write it in as a curly braces, and then e1, e2, e3, e4, e5, and so on. Okay. Now this is an interesting challenge. I want you to type in the chat three kernels. If type type the code, some slide pseudocode kind of thing will also work. The, if for this challenge, three kernels are submitted to the device. Suppose we are submitting three kernels to the device. The first kernel will modify two different memory objects, and the third has a dependency on both first and first and second. Now, how will you manage this? You can either use wait dot in order, or you can depends on. I mean, you can use any of this. I will, I will just I will just take 5 minutes break. You can just type the answer in the chat, or whenever or just now you can also unmute your mic after 5 minutes and just tell me what is the answer. But I would like you to think and come up with it might not be the perfect syntax, might not be the correct code. I will not check it as syntax error, or I will just want a pseudo code how it will be implemented, and that's it. So yeah, let's take 5 minutes break, and yeah, you can also type the answer until that point. You can also submit in the chat box and all. Yeah. Okay.
Yeah. Before that, I have a question.
Yeah, yeah.
Shouldn't the developer ensure that all the commands or transfers, in different kernels
Transfers.
execute in correct order before itself?
So which where are you saying this?
I mean, in
I'm not.
if you go back to the previous slide,
Yeah.
the depends on.
Okay.
So
This.
yes, I think it's the user's headache to enqueue all the commands in the queue in the
Yeah.
correct order.
Yeah. Yeah.
So what is
Developers job.
the
Yeah.
depends on? I'm still not understanding the depends on part. Um,
Okay.
when if you say wait for the event to complete.
Yeah. So you
So
are not getting the dot wait also, right?
yeah, I got wait.
You got in
But how
order
is
also.
the
You
order ensured if the uh, How can
How can means could you clarify your question? Where is your specific
maybe
where?
once I have
Yeah,
the real example, I can understand. But mostly weight I understood depends on, I think, even before submitting or deciding this command will go into the queue for data transfer. Say if there are two different kernels and they have to execute in some order,
yeah,
then I think the developer must decide which command will go into the queue for transfer, um, instead of coding it explicitly. Is that right? Or
yeah, yeah. You are no, but how can you assure the? How can the user assure that after this is executing?
okay?
So this is where we are. So you understand why do we require dot wait, right?
Yes,
So we are just waiting until the kernel task has been completed, right?
yes,
So now what happens if understand this point in using the developer's point of view, right? Suppose you are writing the code, for example, then you have written some you have launched some kernel earlier in the code above, and then you have done some other kernel task, and they both are independent, right?
yeah,
Okay, then you are again doing some third kernel task which is dependent on kernel 1, okay, but it
okay,
is not dependent on kernel 2. So you're understanding what I'm saying.
yeah,
so
yeah. Okay, I
so
see
there,
what.
yeah.
Got it.
So now if you are using the q dot wait, so you have to so basically what you have to do is you have to do that after kernel 2 q dot wait, because you have to wait for the first kernel to complete.
Okay,
So or you have to assign it to the earlier, but you cannot specifically say from the q dot wait that I want this only this kernel to complete, and then it can start executing.
okay,
So do you understand where the dot depends might be helpful?
got it.
Yeah,
Yeah, probably
yeah,
we'll need to execute some examples, then
yeah.
I'll
So
get more
that so
clarity.
that so that I will strongly suggest you to do this, because this is the thing that will be helpful to you. So this is the code which I am saying, right? Suppose you can just what you can do is you can initialize one matrix above. So that can be also you can do it also in home. You can so in the first kernel what it will do, it will do initialize the matrix, right?
Mm.
And then another kernel will initialize the second matrix. So we will
Mhm.
create two matrices, and what the third kernel will do, it will just square all the
Okay,
initialization that you have done in the first kernel.
got it. I see. Those three
Okay,
are three separate kernels.
yeah, three separate kernels you have to create. So there will be two matrix. The kernel one will initialize matrix one. Kernel two will initialize matrix two. Kernel three will square the matrix one, and kernel four will square the matrix four. And I want you to all work with parallel.
Got it. Got it.
If you will do this example, you can just try all the dot wait function in order function, and then you will. So I'll also share the I mean the you know that you should know. I will also share you the code. How can you measure the time? So before the kernel execution, you will just start the time counter, and after the execution, we will stop the time counter, and then you can see the differences between each and every execution that you have done.
Okay, sure.
Okay, okay, yeah. So let's meet after 5 minutes. Until that, you can give the you can solve you can give the pseudo code and something for this challenge, right? So I'll just give me 5 minutes. Yeah, so did anyone get any idea of how to do this, how to solve this problem? Yeah, so Saurabh, you are correct that this answer is correct. Yeah, any other approach? Yes, yeah, definitely. That is also correct. So did everyone else get the differences between in order, weight, and depends on, right? Everyone get the idea of where can we use depends, weight, and then in order. Okay, and I would also like you, so I would also want you to try out that example that we have talked. I in person had just discussed it now, only just before this break. So, so you will, so you will just basically create four kernels into two arrays. Let's assume we will create two arrays of one D array. And now what you will do is for so kernel, so now you will create four kernels in sequential: kernel 1, kernel 2, kernel 3, kernel 4. Kernel 1 will initialize matrix of matrix 1. Kernel 2 will initialize matrix 2. Kernel 3 will square the value which you have initialized at kernel 1, and kernel 4 will square the matrix 2 which you have initialized at kernel 2. Okay, so I want you to try out this example at by on your own, and tomorrow we can discuss this. I mean, how can we do it? And okay, so that will clarify your more doubts in this, because so if you're this is a basic, I mean, tip for you. If you want to work in parallel, then you should be sort of good in this, how this data is going here, how this data is going here. Okay, here can be the data race problem. Here there is data dependency. Is the data dependency taken care of? Even if I'm not writing q dot weight, is the data dependency taken care of? So you should have you should think about these various concepts, small things. It would be helpful for you to become a great developer. Yeah, there any doubt, Pratmesh? So any other has anyone else have done this? And anyone else have written the pseudocode, and so can they can also share their ideas. How can they do this challenge? I will just wait for 1 minute if any other want to share their code or any ideas. Okay, so let's move ahead. I do so is I'm asking. So I want you guys to engage with some of these challenges at least. If you are making the mistakes in the challenges, that's okay. I mean, everyone makes the mistakes. You and I make mistakes a lot. So that shouldn't be any issue. Yeah. Okay. So this is the one way which so Saurabh has said. So in what I can do is so I just copy paste Saurabh's code here. So just joking. That if there is two, I've just taken two kernels E1 and E2, and then this depends on queries here, and then also so I've just written this in two ways. So it's I'm just basically using the depends on kernel. But yeah, of course, as the Saurabh has shown that we can also use dot weight here. Yeah, so Is there any doubt here? So after kernel 1, kernel 2, there could be a dot wait, or we can also use dot depends. So is there any doubt in this approach, or do you have any other approach which we can? Okay, okay, no doubt. Okay. So yeah, so yesterday someone has I was going through the lecture and someone has asked. So yesterday, what we have done is that we have. So most of you have said that we can do the sum only using CPU, right? So can you think of any efficient way how we can do the sum using GPU effectively? I mean, obviously effectively. I mean, as you guys should know that the CPU's thread are faster as compared to GPU threads. GPU has more number of threads and we can run parallel tasks, but the CPU threads are faster. So if you wanted to run any sequential code, then the CPU will run the sequential code faster than the GPU. So I would want you guys to think of a way how can we do the sum effectively in the GPU. So do you guys have any ideas, any topics? How can we do this, or any small concept, or anything you can share it? Anyone? I think yesterday only someone suggested this approach, right? So we will just make 4 3 add 9 and 9 plus 3 5 plus 7 3 plus 2, then you will get this array, then you will further reduce it, further reduce it, further reduce it, and in the log n step we will just get the sum. So what do you think? So can we implement this in GPU? So someone of you only gave this idea right yesterday. Yeah, I mean you can use direct Sycl, but then yeah, you can use Sycl reduce directly, but that won't be efficient too. I mean, so it won't be great for learning perspective, right? Uh, So that's an inbuilt reduction technique, and that will also internally do this thing only. But it would be better for initial to understand. So example, if your standard libraries, STLs, right, in C++, sort and everything, but you have to just go through the basic concept of sort, how sorting is work to get a to get the learning, to get how this algorithm is implemented. So it wouldn't be great. Yeah, you can. So also, but it's good thing to note that you have to search this small thing that can we reduce this? What are the libraries Sycl provide? What everything D++ C provides? Yeah, but what do you think? This algorithm, this way, will it work? Will it be fine? And no problem. I will understand you. What is this barrier here? I'll get to know. I will get you that how this barrier will be used and why the barrier is required and what is a barrier. This is all. So can any one of you just write a small for can any of you know just unmute your mic and tell me that from this index to this index we have to so each what at each iteration what each thread must do to to achieve this task, because now we are properly thinking on the perspective of the code. What do you think that each thread, suppose each thread is assigned one index, so this is thread 0 1 2 3 4 5 6 7, so this all 7, and what each thread will do, can any one of you have any ideas or any hint, or can you think of what each thread should do in each iterations? Suppose this is iteration 1, this is iteration 2, this is iteration 3, this is iteration 4. What should each thread do in each iteration to get the answer? Anyone? Yeah, yeah. So that is what a barrier is. Each iteration should wait. We will come back to it. Each iteration should wait until all the threads have completed the above previous iteration. Yeah, we will come back to that. But it is, yeah, it is help. It should be there. Otherwise there will be some data race and all. We will come to that. Yeah, definitely. But I want to tell me what each ad should do in each iteration. So let's make the problem simpler. Apart from doing this, can you solve this problem? So suppose this is an array. So this 4 will add the sum 5. 3 will add to 7, and 9 and 3 will be summed. 3 and 2 will be summed. Now this 9 and 12 will be summed. 10 and 5 will be summed. Now these 21 and 15 will be summed. Can you just tell me that from where what each thread should do in each iteration? Can you come up with some logic or any kind of, even if it's forced, even I don't want you to write in the kernel perspective. Even if you are thinking in the CPU perspective, let's understand. So let's first write a code for the CPU perspective and then we can make it parallelize, right? So let's first write a simple CPU code for this. Can any one of you write what the CPU code for this will work, how it will work? Then we can transit it to GPU and make it parallel. Can anyone know? So it's a basic C++ code, right? Uh, So we will use just the iterations. First iteration, it will take this many, then this, then this. Initialize with threads index and assign variable. What do you mean initialize the with thread index and assign variable? You can unmute and say also, don't worry. It's perfectly fine. So what do you mean by initializing with thread index and assign variable? I'm not getting it. So I mean I'm not asking you any difficult task, right? This is just the CPU. So I want you to write the code for the CPU only, CPU part only. I don't want you to write for the kernel. So you can just write for using the for loops and all. You can just write this code. Is does anyone have any hint? You can also unmute and say it's completely fine. Okay, so I will give you some hint. Suppose we consider only starting. So let's consider that in this first iteration we are looking at 8 elements, right? So this is n numbers. We are looking at n numbers, and in the second iteration we are looking at four numbers. You can see, so n by 2 numbers. In the second iteration you are looking 2. In the last iteration there is only 1. So this is a small hint I'm giving you now. If anyone can use bisect method. I'm sorry, I don't know what is a bisect method. Can you elaborate that? Yeah, n by 2. Okay, every time you will just n by so you will initialize some array by n and then you will just do divide it by 2 each iteration, right? That's what you mean by bisect method, right? So yeah, that is the correct. That is what we are basically doing it. But in the for loop, suppose now let me give you it. One more end. So let's consider this four elements only. In the first iteration, we are considering only n by two n by two threads only. Other all threads, I don't it doesn't matter with me. So I will consider n by two thread. Each thread will add its spawn position plus the n by 2th of the next of the forward. So suppose this is at index 0, right? So the currently n is 8, right? So this is at index 0. Now this will add 0. And so this is at zeroth value at zeroth index and fourth index, right? 0 plus n by 2. This is 1 plus n by 2 equals to 5. So this will add at index 3, index 7. So 0, 1, 2, 3, 4, 5, 6, 7, right? So I'm using 0 based index as it is in C, as it is by default, right? So it will just add from index 0 and plus n by 2 at each iteration. Now, now what happens is our n will reduce by a from 8 to 4. So from this 8, n is reduced to 4. Now I will initialize I with n by 2 again. So n by 2, so it will be 0 and it will just take 0 and 1. And from that, so this will add 0 plus n by 2. But now our n is 4. So 0 plus 4 by 2 means 2. So this will take 12. So 9 plus 12, 10 plus 5 similarly. So this way in the CPU can do the process. The same thing which instead of using the for loop, can we just add a kernel to it? So there will be two for loops, right? Suppose if I wanted to do the task, there will be two for loops. One for loop is for this each iteration. There is one for loop, and if I'm using the CPU code, and there is another for loop which will be inside the this iteration. And each iteration you will travel from 0 to for loop from 0 to n by 2. Each element you will do operation, right? So it will add the element at index I plus index n by 2 plus I. So this is the two operation that we will perform, right? So is anyone having any doubt? So there are two for loops we are using. Now suppose I tell you that I can parallelize this inside the for loop which is inside the nested for loop, right? The nested one. So what I have done is so I have taken the outside for loop so suppose I have taken iterations, right? Now for each thread I have so each thread will run on its own, right? So suppose I am passing total 9 threads, and what each thread will do, it will do the for loop from offset. So it will start from n by 2 and it will go to 0. So initially what I have suggested, right? The first iteration there are, so from these 8 numbers we are selecting 4 numbers, right? So the offset will be 4 and it will go until 0. And it will sorry, this offset should reduce here. I don't know why it's plus plus, it should be minus minus here. It's a small typo. And if okay, so now I'm launching the threads as n, right? But if you are noticing that the 5 7 3 2 threads are uh, not computing anything, right? So how can we make them that if it is not computing? So I will just select that if the thread index is I is less than offset, then only it will do the computation. Other thread will not do any computations. So in the first iteration, offset will be n by 2. So this 4 threads will work. So as the offset will be 4, and then from that fourth then 4 only the that 4 will only go inside this if block, and then it will compute its current index plus I plus off the index or offsets index, right? So is everyone getting this concept? Yeah, here is a slight typo. It should be offset what should be the it's an interesting question. What should be this year offset apart from the, it shouldn't be offset plus plus, right? Otherwise it will be an infinite loop. What should be here, instead of offset plus plus? What do you think? Offset minus minus? What do you, are you sure that is offset minus minus is the correct answer? If you can just run a second iteration, then you can figure out that offset minus minus might not be correct. If you are using the second iteration, suppose in the first iteration we are selecting 4. In the second iteration, I told you that we are selecting 2 elements, because from this 8 we have reduced our problem size to 4. Yeah, definitely, sir. It should be offset equal to offset divided by 2. Correct. That's it. Yeah, it should be offset equals to offset divided, because we are reducing our total number of whatever the elements by 2, right? Every time we are adding 2 elements, so it is the size of the offset should reduce by 2, divide by 2, sorry, not reduce by 2. It should divide, divide its value by 2 every time and every moment. Yeah, reduce by half. Yeah, definitely. Up, so yeah, so I will just write offset equal to offset divided by 2. Then this code will work correctly or not? What do you guys think? Will this code be fine? Will this give the optimal answer? Will this give the total sum, or it will face any problem? Will there be any data races, data dependency stuff that we have studied today? So I also wanted to ask you, how many of you guys that doesn't know that what is a data race? So I haven't gone into detail of what is data race. How many of you guys don't know what is data race? Is there anyone who doesn't know what is a data race and where the data race occurs in the threads? How can it occur? So I will just explain you in brief. Okay, yeah. So data race will occur when, suppose when there is a read write conflicts. Suppose what happens if 2 elements are writing in the same place. What will happen? What do you think? What will happen? Both two threads are writing on the same index, on the same value. So there can be only one of the value will be there. Either, so suppose kernel 1, so suppose thread 1 is writing 2 and the thread 2 is writing 3. So either 2 will be there or either 3 will be there. Anyone who is the last will be the value. So this is a typical example of data race. Now suppose the data, also the data race can also occur when you are reading and writing. Suppose thread 2 is writing something and thread 3 is reading something. So now what happens is thread 2 has written something. So suppose the initial value of that element where the both of them are writing, and suppose the initial value is 0. Now the thread 0 is writing 3 here and the thread 1 is reading it from here. So what will happen? So 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 the thread 1 will either read 0 or 3. So there is a data race here, right? It is not consistent that either he will read, so it can be either he will read 0 or he can read 3. Any one can be true. It depends on the data race. Whoever comes first will be the, according to that, the answer will might differ. So this is the basic ideology of the data race and how can data race occur. So does it clarifies? Okay, yeah, race conditions. Yeah, race conditions similar to the DBMS. Yeah, similar to race conditions. There is a data race that can happen here. So do you think that data race can happen in this code also, or the data race will not happen in this code? Can anyone is anyone finding any problem or any data race, data dependence, or any sort of confusion here? So I would suggest that there is a data dependency here, and I will tell you how there is a data dependency here. So suppose now what happens is, so suppose consider thread one is working on its own, and thread one, thread zero, and thread zero and thread one, right? So thread zero and thread two. Let's take thread zero and thread two. So thread 0 in the first iteration will add 4 plus 5, and the thread 2 will add 9 plus 3. In the first iteration, these both are working in parallel. So what could happen is that the thread 0, this thread 2 might thread 0 might have computed 4 plus 5, and it has updated its value to 9. But the thread 2 have not updated its value 9 plus 3, and it has not updated its value 12. So currently index 2's value is 9 and index 0's value is 9. Now now what happens if the thread 0 start executing the code, start executing second iteration. In the second iteration, what he will do is he will add its current value plus the second value, because it's now the n is 4, so it's n divided by 2, so 0 plus 2, 2. So he will add 9 plus, instead of adding 12, he will add 9. So he will add 9 plus 9. So this, and then the thread 2 gets updated to its 12. So can you understand, there is a data dependency case, data race case kind of situation here? Is everyone getting this data race, data dependency kind of issue which we are facing here? Yeah, so yeah, because thread 0 has started its second iteration, while the thread 1 has not completed first iteration. So we need some sort of barrier kind of thing. Apart from starting from first iteration and second iteration, there should be some barrier concept, right? From 1 and 2. We will study the proper barriers in the first, but I would like you to, I mean, start imagining this kind of concepts, this kind of things, and all of basic concept which you might be facing earlier. So if you started some writing some codes and all, but you should be aware that this kind of situation might occur, this kind of situation might occur. So there is something we have to make sure that all threads have completed addition before reducing by half. Yes, correct, Saurabh. We have to make sure that the all the threads has completed their iteration one before I start executing second iteration. We cannot start executing second iteration until the first iteration is completed. Yeah, you are correct, Saurabh. So this is the thing which I want you to guys think, and this is very interesting concept, how the GPU can behave in different ways which you might not have intended it to do. Is this code correct? False. But now I change something. Suppose, so let's see. Now I have just taken this for loop outside and pushed this Q part inside. So this kernel part inside. So in every iteration I am calling a kernel. Now is this code correct or false? So yeah, of course, this is offset equal to offset n by 2. Apart from that, is this code correct? So what do you guys think? Is this code correct apart from this? Any thoughts, any idea? Now what we are doing, so we are first in one, we are only assigning one kernel, and we in the kernel we are using the for loop. Now I've used the for loop outside. So each iteration I am calling one kernel, and then it will start executing. What do you think? This is, will this code work correctly? I mean, there are only two answers, true or false. I mean, so I want everyone to give the, I want everyone to engage in this discussion. So it seems like, yeah, so it seems like this code will give the correct answer because, or it will not give the correct answer. It will give the correct answer if we just add a small thing here. I want you to guys think about what could be that small possible thing which we will add here so that this will give the correct answer. What will be that thing? I'm telling you that this code will work correct answer. I will just need to do a slight modification. I will to just add a small function, then it will start working correctly. This is a small int. Can you guys figure out what should be that thing that I can add? We have just studied that in the today's class only. Yeah, dot wait. Yes, definitely dot wait. If you are not using the dot wait, then what will happen is the CPU will start calling all the kernels and then it might fail. So this code is also not correct. So we have to add here dot wait and here offset, of course. So then this code will start working correctly. So do every guys get the point? So do everyone get this idea that how this whole we can do the sum? And I would also like to you to try this code by yourself. Then how this is how if you are using this, then we are getting this dependency. How we are getting this, then we will getting this dependency. So I would like you to guys think in that way. Yeah, this will, if we are adding dot wait here, then it will work completely fine. Yeah, I agree with that. Okay, so yeah, I also want you, so now I want you to, so yeah, so I'm completing today's class, but I'm giving you to think something. How to compute the prefix sum. So we know that the prefix sum, right? The basic prefix sum things like 4. So suppose the array is given this, then the prefix sum is 4 plus 3, 7. Then it will be 7 plus 9, 9 plus 3, 19 plus 5. So this is also a similar kind of reduction. And the thing which we have done here is called the reduction. That is why the Sycl, in the Sycl, Prasanna has just given us the code, right? The Sycl reduce. So this is why it is called. So we are reducing the elements, number of elements which we are processing by each iteration. That is why it is called reductions. So I want you to guys to think about something that how can we implement this prefix sum? I mean, where can we get the data arrays? Where can we have data dependencies? Can we get this? Where do we need to write dot wait? Where can we use this and everything? And yeah, I would like you. So anyway, so the prefix sum can be this and this also. I mean, any prefix sum which you want can be, if you can compute, you can either start with 0 and you can either start with first index and then start the prefix sum. It's fine. It doesn't matter. But yeah, I would like you to think in this concept. And we will discuss this tomorrow. But yeah, I would like you to have some approach. Have you done some try and error? Have tried to do this? I tried to solve this. I also suggest you to run this code so that you can get some more clarifying idea. And yeah, I would also recommend to create a large size array. So what you can basically do is you can create an array using CPU. I mean the normal prefix sum you can compute, and then you will just try then you will just run your code and then you will compare and then seeing. So I would just suggest you to go up to 10, 5,000, 1,000, 5,000 length of array and just test it. That is it working correct? If it's not working correct, where could be the problem? Yeah. So is there any other doubts regarding today's lecture? Mm. And guys, I want you to be more involved in these conversations, because then only, I mean, it will be beneficial to you as well. Yeah, you should try out prefixum on GPUs on your own. So how can you? So I wanted to also write the code for that. If you get the time, if it's okay. I mean, if you can't get the right time to write the code, you can just draw something you can do here and there, and you can come up with what could be the solution for this. Okay. So it's nice. I hope that I have given you some thoughts for you to figure out and for your brain to work on. Thank you for joining, and yeah, see you tomorrow.